So we are now in my IntelliJ project for the case study EX36 example. If you click on this example, you'll see that this particular example creates a bunch of set objects that contain the unique words in the complete works of William Shakespeare. And this will show you a bunch of interesting things. It'll show you the difference in overhead between collecting results in a parallel stream versus a sequential stream, using both concurrent and non-concurrent collectors for various types of Java set implementations, including HashSet and TreeSet. And we'll also see that there's a concurrent variant of this as well that's really cool. So I'll start running the program in the background because it takes a little bit of time to run. And in the meantime, we'll take a look at the assignment or the solution itself. So we have this functional interface called quad function. You'll see how quad function gets used later. As you can see, it takes 4 parameters and returns a return result. We're going to run the program for a max number of 5 iterations. We could change this just to get it to run more times to see the difference on the average over time through multiple runs. And why do we do that? Just because running it one time might not be enough to demonstrate the differences between the different approaches. We have a link to the complete work of William Shakespeare, which appears here. And this is a very large file. You can see it's about 5.5 megabytes that contains all the plays, all 37 plays, and all of the sonnets from William Shakespeare. And then I have this really crazy regular expression, which goes ahead and will split the works of William Shakespeare up into the words in William Shakespeare. And that's a really cool, fun example of regular expressions. And then all those words will be processed, and we're going to collect them into sets, so we'll end up with unique words in Shakespeare. When we run the program, you'll see that it's going to print out the number of available processor cores. You take a look here, we have a total of 10 cores available on my MacBook Pro. First thing we do is warm up the thread pool, just so that the test will be more accurate. And then we run 2 sets of tests. The first set of tests is going to use HashSet as the type of set we're collecting the words into, which of course will be unique, but it'll be hashed. And so there's no particular rhyme or reason to the order in which the words appear. The second set we're going to do is going to be a tree set, in which case the words that are unique, of course, will be sorted in ascending order. And a tree set uses a balanced binary tree. I think it uses some kind of red-black tree-like implementation. You can also see we pass in constructor references for the various kinds of sets we're making here. So here, this one's going to use a hash set for the non-concurrent collector, and something called concurrent hash map key set view. And a key set view is a concurrent set that uses concurrent hash map, but it maps it into the set style with just a key. And we're going to use that to collect things in a concurrent collector. And then down here for the second set of tests, we're going to use the tree set, and we're going to pass in tree set constructors for both concurrent and non-concurrent collectors. And you'll see how we make that work in a second when we talk about the concurrent set collector, which is something else kind of cool that we're going to talk about. Okay, so that's basically the idea, and this is the way the test actually works. So it's going to go through the complete works of William Shakespeare. We get the complete works of William Shakespeare with this little helper function, which takes a file name and the splitter regular expression and the number of words we want, starting from the beginning. And so it's going to open up this big file of the works of Shakespeare, read it all into one big buffer, so all 5.5 megabytes will be in memory in one big string. And then we take that string and we split it using the regular expression, and we'll split it into a stream, which means we'll have a bunch of words that come out, and those words will then we'll filter out any empty words, and we'll go up to limit of them, and then we'll collect the results into a list. And that will give us the result that we're looking for here. So let's pop back over there. So we get all the works of Shakespeare into a stream of words. Now, these will be non-unique words. By the way, this is where we pass in that crazy regular expression that we use to split things up into words. I won't bother trying to explain it all, but it's basically just getting rid of all the non-character symbols and using them as the splitting of the words. We then go ahead and apply the parameter that's passed in here. Now, this is kind of a fun parameter. Check this out. This is neat. This shows the power of Java functional interfaces. So what we're passing in here is a method reference to a method called TimeStreamCollect. And here is the TimeStreamCollect method. It takes the type of the test, it takes whether we're running in parallel or not, it takes a list of words, and it takes a collector which will collect the results. And so you can see it takes 4 parameters and it returns void. I use the word return in air quotes because it doesn't really return anything. We just need that there for syntactic purposes. So if you recall before, we had something that was called a quad function. There was the quad function. And down here, what we have is the parameter for run set collectors is a quad function that takes a string, a Boolean, a list of strings, and a collector, and returns void. And that happens to be exactly what the signature of TimeStreamCollect is. So TimeStreamCollect has that signature, and therefore we can pass a method reference to that particular method as the 4th parameter to run set collector tests, which expects to take a quad function as its last parameter. So that's what collect is. It's its quad function. And what we're going to do is we're going to say, please apply that function, and we're going to pass in whether we're running it with non-concurrent or concurrent. And we're going to go ahead and indicate whether we're going to be running it in as a sequential stream or a parallel stream. We pass in the words we're going to be processing, and then we pass in the appropriate collector. And this, in this particular case, we're going to make the collector be just a collection that takes whatever's passed in here, which is either going to be the new tree set or the new hash map. So that's what we pass in for those. And then for the concurrent set collectors, we're going to call a factor method called toSet, which is on concurrent set collector. We'll talk about concurrent set collector here in a minute. And then we pass in the concurrent set supplier. And notice that the set supplier is passed in as a constructor reference, and that knows how to make the appropriate type of collection. So you can see here we have constructor reference for hash set, constructor reference for concurrent hash map, key set map, constructor reference for tree set, and so on. So that's what we're passing in there. And so these things will then be called to get the appropriate collections we're going to be collecting into. Now here's what actually gets called. This is the TimeStreamCollect method, and this is the one that's going to do all the interesting work. The first thing it does is it runs the garbage collector, and that means everybody's test starts out with all the memory available to it. We then figure out what kind of a test it is. Is it parallel? Is it sequential? And then we use our little timer run method, which, as you probably have seen by this point, keeps track of how long it takes to run this particular supplier that's passed to it. Just a quick recap. Here's time run, which takes in a runnable, and it starts the timing, runs the runnable, stops the timing, and then it stores the results into this map. And the map is keyed. The keys in the map are the test name down here. And you'll see when we look at the results here in a second that that's what gets printed out here for the results, printing the results here. Okay, so if we come back over here and we take a look at this, this is where it gets fun. We create ourselves an array list that's empty, and then we use the intStreamRange method. This is basically the functional way of doing a for loop. So we iterate from 0 to up to, but not including S-max iterations. And for each element in that range, we go ahead and we take the words that are passed in, and we conditionally either turn them into a parallel stream or a sequential stream. And then we are going to modify each string. So what we do here, this is just to kind of burn some CPU cycles. We take the string, this is a word in Shakespeare, and I probably should change this to word because it's really a word. It is a string, but it's a word in the context of what we're doing. And what we're going to do is we're going to uppercase the word. We're going to do a rot13 on the word, which is just a way to burn some CPU time. I don't know if you guys know what rot13 is, but you take every character that's a letter and you shift it by 13. So it's kind of a way of encrypting the data. And then we lowercase the results. And we probably, if we really wanted to be fun, we could then go ahead and rot13 the results of that once again. So we'd end up moving it back into what it was before. There are 26 letters, so that's why we rot13, which shifts them over by half. This is just to burn CPU time. And then we convert the stream into a list, and we add this to our overall list. And we do this S-max iteration times. And that's just to get an average of the results. So what we're going to do now is take a look at the results, and then we're going to come and take a look at the concurrent set collector, which is really quite interesting. So here are the results from this run. And you can see we do this first for hash sets, and then we do it for tree sets. And we start out with 1,000 words of Shakespeare, then 10,000 words of Shakespeare, then 100,000 words of Shakespeare, and then ultimately all the words of Shakespeare. And what you can notice here, again, this is just kind of interesting, when there's a small number of words, the sequential stuff actually performs better, which is what we've talked about many times. If n is small, sequential will dominate. When n gets bigger, however, then parallelism starts to pay off. And in fact, as you can see here, when we get to all the words of Shakespeare, and even when we're at really 100,000 words of Shakespeare, the parallel solutions are beginning to win. And win here means lower number, because it's taking less time to process this stuff, to find the unique rot 13 words in Shakespeare. And so what we end up with here at the end for the hash set results is the parallel collector performs the best, almost twice as good as the non-concurrent version for hash set. And then the sequential stuff is way behind, all that stuff. For tree set, we see the same results. We see parallel eventually dominates. At the beginning, sequential dominates when n is small. And again, the difference isn't quite so much. We'll see why that is when we look at the code. It's not quite as good for tree set for some reasons that will become clear in a second. But you can see that parallel still wins when n is large. And if you take a look at the magnitude here, you can see that 195 milliseconds for the concurrent tree set and 135 milliseconds for the concurrent hash set. And keep that in mind when we take a look at the collector set, the set collector that is going to be doing all this stuff. And we'll take a look at that in a second. So key takeaway points from looking at the results. As n gets larger, parallelism begins to dominate. Concurrent collectors can be an improvement over non-concurrent collectors when the time to collect things into a concurrent collection, or a mutable result container as it's called in the collector framework, is faster than merging complex data types like sets, in this case either hash sets or tree sets.